Would you get?
Tell you all about it.
So what am I gonna do?
Help preach you.
So like, you find out. Play tennis.
But not, it's not like the boat race.
Yes.
Snatch out. Yeah, that's one.
How much sense that they did it?
And you know, over your race.
Yeah, they use yours.
Over there, it's like.
I mean, like, how much? Oh, I just think there's weird on like.
There might be, like, oh, you can get everything.
It's like kind of.
I was like, it's a good way, yeah, there's no pretty well. But it actually, pretty much.
Great.
Water.
So sorry that you never explained those.
Oh, my bad.
The fossil or something.
I'm sorry.
A little bit. They're not saying.
I think that was just because it's straight. Question in there, so.
Yeah.
Do you have to know? Like this thing's sort of.
There's like one that's like two songs.
It's okay, I feel my friend yesterday, she was like, that city school is so bad. They're all just like stupid, honestly, it's such a big deal.
All right, so let's start with our test review. Now we have a piecewise function here, and we're going to be asked to evaluate the limits as we approach either a numeric value or, yeah, plus or minus infinity. Now, we have to be able to first pick out which expression is going to be suitable for the function we're working with. And then we have to go through our steps. Right? Remember our steps. If it's a real number, plug in the right substitution. If it's infinity, we compare degrees. Right? So we never want to do decimals or 100 unless that first step tells us to do that. Our initial step tells us to do that. I do want to point out a couple of things here as well, that we have piecewise function here. These are all mostly connected parts of graph. You have a linear graph to the left of 2. You have a linear graph between 2 and 5. You have a linear graph to the right of 5. But what about these two? What are these two here? These are just what? Points. Okay, so I want us to identify them as points. And I also want us to understand that limits do not follow points. Limits follows the connected parts of graph. It doesn't look at points. So anytime you're evaluating limit, you may be tempted to want to look at the 2 and 5 because there's approaching 2, there's approaching 5, but limits. We don't want to involve limits when we're dealing with points. So keep that in mind. All right, so part A, I'm gonna put on a separate sheet just so I can have enough room to show limit as x approaches negative infinity. So that means we're following graph to the left, negative 100 along that interval there. So which interval is going to be will be still there if we're all the way to negative infinity? Which piecewise will be suitable for? Good, because we're talking about anything to the left of 2 is going to be looking at that x plus 5, right? So go ahead and put the x plus 5 there. And what do we do when we see infinity? Wait, what do we do? What's our first step? Compare what? Compare degrees. Now, we don't see a denominator, right? So, but we can force the denominator to be what? 1, right? So, what do you notice?
So we're no.
Yeah, so which has a higher degree numerator, which means it's either what? Good, right? So we compare degrees. We realize the top is growing faster. Obviously, the denominator is not even growing at all. So this fraction is getting larger and larger over time. We know that it's either positive or negative infinity. Now we can test a value in the direction that we're headed. What can we test? Yep. And then we have negative over a positive. So negative infinity. Okay, part B, limit as x approaches 2 from the left side of 2. So which graph is approaching 2 from the left side of 2? Still the first one, yeah. So x plus 5 is going to be all the way up until 2. So all right, so what's our first step for if we're approaching a real number? Plug in, right? No decimals. We're just plugging in the 2. And what do we get? We get 7. That's it, right? There's nothing. The limit exists, and so the one side limit will also fall right into place as well. And we only deal with decimals if we realize our direct substitution is giving us something that tells us there's a vertical asymptote. Part C. 2 from the right. So which piecewise function is coming from the other side of 2?
2x.
2x minus 1. Okay. Again, direct substitution. And we get 3. Good. And we're done. Yeah. Part D. Limit as x approaches 2 of g of x. Now, how do we think about this one? Does not exist. Notice that obviously we don't want to look at the 2. We don't want to say it's 11, right? That's just the point. That point is like an island. It does not involve limits. The limit never follows the order pair. But if the limit is going to exist, there has to be an agreement on both sides, right? And we see that there is no agreement. So therefore, we can say that the limit does not exist, right? One side is headed towards 7. The other side is headed towards 3. There's obviously a disconnect, and therefore limit doesn't exist. Yes.
The left limit and the right
Mhm.
limit would be right, but the left limit does not equal.
You don't have to go that far. Technically, I think I'm going to ask for more work when we get into like continuity conditions. But for this one, you can just say DNE. You don't have to show your reasoning. Yeah. All right, good. Part E. Limit x as x approaches 5 from the left side of 5. Which piecewise would be good for that? Still 2x minus 1. Good. Direct substitution. Lots of 9. Good. And we're done, right? Part F. Approaching 5 from the right. Which one do you choose from that? X plus 4. Direct substitution. What do we get? 9 as well, okay. Part G, limit as x approaches 5. What'd you say for this one?
No.
9, right? Also 9. The order pair is living elsewhere, but so we know there's a hole in the graph, but the approach is consistent, right? Left and right are both headed towards 9. And so that's enough for our limit to exist, even though the point is living elsewhere.
If it asked like G of 5 back.
Good. Yeah. If it's asking for G of 5, then we look at that single point and we. All right. Part H. Limit as x approaches 6 from the right. Of which expression? X plus 4, right? Direct substitution, we get 10. Nothing more to do. As we approach infinity, which expression is going to still be there? X plus 4. So what do we do with infinity?
Check the degree.
Check degrees, right? If you don't see a denominator, you can force the denominator to be 1, right? What do you notice? What happens if you compare degrees? Numerator has obviously the higher degree 1 versus degree 0, which means this fraction is getting larger and larger in one of two directions, either positive or negative infinity. And now we can test what? 100. 100 into the expression, I get positive over a positive, so therefore positive. All right, questions so far? All right, number 2. Use continuity conditions to determine if the function is continuous or not continuous. If not continuous, identify the type of discontinuity. So we're going to go through our conditions. So find your point, evaluate your limit, and see how far you can go. If you see one side of limit, sorry, if you see greater than or less than, you know you have to involve one side of limit, right? Okay, so go ahead and step through your conditions, and then I'll work alongside you guys. I do have the keys attached in this packet, so if you're working ahead of me, you can always check your progress. Make sure you show the notation of evaluating each of the one-side limit, that you put the expression that you want to evaluate, and that you do direct substitution. You don't have to say that these limits are not equal. From here, you can just make the conclusion that the limit doesn't exist. Make sure that you include f of x to indicate that you're talking about this function when you're you're talking about the limit of that function. And therefore, if the second condition fails, we stop. We know what type of discontinuity. It's going to be a non-removable discontinuity. Make sure you specify the location at x equals 3. Number 3, find the k-value that will make the function continuous. So now we're going to use continuity condition as a problem-solving tool, as a equation-solving tool. We're just going to walk through our conditions, and then eventually we're going to be able to solve for k just by the nature of our conditions. But the piecewise looks a little different than number 2, right? And how is that going to impact the way we do our conditions? Good, no one-sided limit. All we need is one limit statement, and that's just for the graph. The graph is all contained within x doesn't equal to -3, because this means left of -3, right of -3, it's all looking at the same graph. So there's no need for one-sided limit here. But you're just going to step through your conditions, and then you're going to be able to solve for k just by going through your conditions.
I think myself, if we don't specify the f of -3 equals k, like if we just know that. I didn't write it, but I got the right answer.
I just want to see your work. I think I am going to specify that. Show me the conditions. So this is just going to feel like a quiz problem, right? You're just going through your direct substitution. There's a whole factor, then evaluate. I keep going. My limit passes, but I need continuity. I need all 3 conditions to pass. So that's going to force me to set these equal to each other. And I'm going to solve for k just by going through my conditions. Page 2. You see the half page there, 1, 2, and 3. This should feel like what we did on the quiz. So go through your steps, go through your direct substitution, confirm that there's a 0 over 0 before you do anything algebraic. So we confirmed there's a 0 over 0, there's a hole, we can factor. We know what we want. We want the x minus 2 and 2 minus x to cancel out, but what do you notice though? Are they a perfect match? But they're close, right? I can cancel that out. I can cancel them out. I just need to make sure what remains. -1. You can either factor a -1 to get them to look alike, or you can just cancel them out and know that there's a -1 that still remains. And then direct substitution. This ends up being x minus 9, which is going to be a perfect fit, perfect match. Numerator goes away, but there's still a 1 left over up top. Now, the final step, direct substitution. Okay, number 3. Okay, your first goal is to try to get that numerator fraction to merge into a single fraction. And again, we can worry then about how to resolve that complex fraction. So there's my updated complex fraction after I merge the 1 over x minus 1/2. Now we can think of it as this dividing by x minus 2, and same thing as this multiplied by the reciprocal of x minus 2. Okay, we know what we want. We want the x minus 2 and 2 minus x to cancel out, but they're off by a factor of -1. I can show the -1 factored out to be the same, or we can just cancel them out and understand that there's a -1 left over. Make your final direct substitution. 2 in for the remaining x. All right, number 4. Very similar steps as what we did before with continuity condition and solving for k. Any questions up to 4? So number 5, we have we're trying to solve for a and b, but we also have a graph in front of us, and I think there's certain things we can gather about the graph. So if we look at the graph here, some helpful order pairs that we can pull. One is x-intercept, so that's something that's going to be helpful. X-intercept is going to be -2, 0, and 2, 0, right? We can see that from the graph. And algebraically, we know that x-intercepts comes from the numerator, right? We can set the numerator equal to 0 And that will give us information about x-intercept. And that will kind of help us give us some way of maybe figuring out what that a value can be. Another set of information that is helpful is we see vertical asymptotes as well, right? Where do you see vertical asymptotes? X equals 1 and x equals -1. And you know that if I make the denominator equal to 0, that's going to give me information about vertical asymptote. And if we do that, we can kind of work backwards and figure out what the b value can be in that instance. So I know that to find x-intercepts, I would set the numerator equal to 0. I know information about my x-intercept. I already know my x-intercept is at 2 or -2, so I can plug either of them in to x. And they'll give me the same result because 2 squared or -2 squared is going to be the same. And that can help me solve for a. And likewise, if I set the denominator equal to 0, that will give me information about vertical asymptote. But I already know what my vertical asymptote is that x equals 1. So if I plug 1 in for x, that can help me solve for my missing b value. 1 or -1 is still going to give you a +1. Number 6, if you factor everything and then look to see what remains in the denominator, that will tell you where the vertical asymptote is. So number 6 is going to be answer choice B. Oh yeah, I'll work it out. We know there's discontinuity at 1 and -2, but we know 1 is where the hole is, so there must be a vertical asymptote at x equals -2. Okay, any questions? All right, page 5. Another piecewise function. We're going to walk through the same process that we did before. Page 5. All right, another piecewise function to look at here. Part A. All right, approaching negative infinity. Oh, again, let's highlight our points, make sure that that we don't get distracted by these points when we're dealing with limits. Okay, limit is x approaching negative infinity. Which piecewise would be the best suitable? First one, good. Because less than 2, right? We keep going towards less than 2 is eventually in the direction of negative infinity. All right, what's our first step if we see positive or negative infinity? Yeah, compare degrees, right? What do you notice about the degrees? The same, so therefore, what's my limit? 1/2. Good. Part B, approaching 2 from the left. Approaching 2 from the left. Which piecewise do we choose if we're approaching 2 from the left?
The first one.
Still the first one. Okay, good. Right. What's the first step if we see a real number? Direct substitution, right? We don't do anything. We ignore that one-sided limit. That one-sided limit is helpful for us to pick out the expression that we're going to use, but algebraically, it's just a 2, right? Okay, so plug 2 in. What do we get?
7/0.
Good, 7/0. What's happening here? There's a what? Good, there's a vertical asymptote. Normally, you would say that the limit, if this is a full limit, you would just say what? Does not exist, but this is not a full limit, right? This is asking for a one-sided limit. If we're approaching a vertical asymptote from just the left or just the right side, there's, right, it's one of two options, right? It's either going to go up to positive infinity, or it's going to go down to negative infinity. Now we can do what? Now we can plug in test what? Good, decimals, right? Now we can do decimals. Now we can choose a number as we get closer towards 2 from the left side of 2. Now decimals can play a role. So 1.9 in for x. Okay, so numerator, we get what? Positive. Now, we know 2 times 2 is 4. 2 times 1.9 is a number less than 4, right? So we don't have to know what that number is. We know it's less than 4, like 3 point something. 3 point something minus 4 is going to be negative, so negative. Okay, limit as x approaches 2 from the right. Which piecewise do we choose if we're coming from the right side of 2?
2x.
Okay. What's your first step? Direct substitution, and we get -1. And that's it, right? If we get a real number, there's nothing more to do. We have our limit, or one-sided limit. What about limit as x approaches 2? Good. We're not getting distracted by the 12 there. We know the point has no say on what the limit is, but we have 2 different graphs on either side of 2, and we have that data from part B and C. We need these to be in agreement if we want the limit to exist, and they're not in agreement. One's going down to infinity, the other one's headed towards -1. So therefore, I can just say g of x. All right, what about approaching 5 from the left side of 5? Good, 2x minus 5 still. What do you get? 5. Direct substitution, right? Five from the right. What do we choose? 5 from the right. So the last one, okay. All right, first things first. It's your first step. Direct substitution. And what does that give you? Yep, so we know this is a vertical asymptote. You know that the limit doesn't exist, but it's not asking for the full limit, right? It's asking for the approach towards that limit from towards that asymptote from the right side of 5. And that means we're down to 2 options, right? It's either it's doing one of 2 things. It's either headed towards positive infinity or going down towards the infinity. And because we're trying to decide between these 2, now we can do what? Now we can test decimals. All right, so numerator, we would get what? Negative. As we head towards the asymptote, the graph is going to shoot up towards positive infinity. So, part G, limit as x approaches 5.
80.
Good. We're not getting distracted by the order pair. The order pair has no say in the limit. We want to look at from the left and from the right because we have 2 different graphs, and both graphs are not headed towards the same y value. So okay, 3 from the right. Which one do we choose?
2x minus 5.
2x minus 5. Okay, direct substitution. All right, approaching infinity. Which one do we choose for that? Last one, yeah. All right, what's our first step if we see approaching infinity?
Degrees.
Compare degrees. What do you notice?
Higher on the numerator.
Yep, which means this fraction is getting larger and larger. It's either going in one of 2 directions. It's either going to go up towards positive infinity or down towards negative infinity. And now, how do we decide between these 2 options? Yeah, because we're headed to the right, so we want to move off grid to the right, and the easy large number in that direction is 100. Okay. Numerator, we get negative. Denominator, we get negative. 2 negatives makes the positive. Page 5, number 2. Okay, you're going to use continuity condition to see if the function is continuous. And if it's not, then we're going to decide where it fails. And from where it fails, we can decide what type of discontinuity. Okay, everybody good so far? Number 1, no questions? what do we need with the second condition? Less than, greater than, so we need what? One side limit, yeah. There's not an agreement, so we can make our conclusion. Number three, we talked about this yesterday. What's strange about this type of function? Which means how many horizontal asymptotes would you expect? 2, yeah. And there's a plus and minus of the ratio. So first, for number 3, you notice the degrees are the same. So we just take the ratio of the coefficients and just understand that there's going to be 2 of them. A positive version and a negative version.
Can my answer be like y equals plus or minus 2?
That's fine. Yeah, you can also merge it together and say y equals plus or minus 2/6.
Is it just the degrees?
Well, first off, the degrees are the same,
Oh, yeah.
right? And so that's why we can take the ratio of the coefficients.
Well, the degrees are the same, you take the ratios.
Right. Okay, last one for today. Try number 4. Number 4 should feel like a quiz problem. If they're not the same, then it'll either just be 0 or there wouldn't be a horizontal asymptote. But typically, if you see the setup, you're almost expecting there to be the same so that I can test you about the fact that there's 2 asymptotes.
There's not gonna be any questions for, there's gonna be like a high. For the load.
Not with the radicals. Okay, your homework, I think you guys have pretty much finished it just from the regular packet, from the notes packet. You're just going to do page 3740. There's probably only minimal problems that you have to do. So I'll send out a reminder though, but I think you guys are almost finished all the problems there. Okay, we'll do more review on Monday, but I will be available for help session Monday, Tuesday, and Wednesday. So if you have questions, you want me to go over some additional problems, I can help Monday and Tuesday. Wednesday, I'll do a morning help session at an earlier time. I'll send out a reminder on Sunday.
Thank you.
Okay, thanks.
Hey, Jonathan, I see about like, remember the word ends?
Yeah.
Like 10% of energy goes to the next. So, yeah, one of the highest, consumer for the food chain. It's gonna be like kilowatt.
And it's, don't.